Can anybody in the back can hear me well? So probably I cannot use microphone today. I'm gonna follow Omar's advice from yesterday. And also I would like to do like a special thanks to Samaria and Rafael before I forget for organizing this beautiful conference. I know it's a Saturday. I know it has been fruitful, but of course full of activities. So I also would like to thank you for being here at this hour. So the last tutorial was like 3 days ago, so I'm just gonna tell you what I'm going to do today, or at least what is the plan of what I'm going to do today. So I'm going to talk about multidimensional asymptotic classes, which was a topic that we left last time. Then we're gonna say something about like Lógica conjecture and something about stability. There are not gonna be a lot of definitions, just the main idea of what is going on in those subjects. At some point, I'm going to talk about the product of finite receiver rings that will happen later. But let me start with a quick recap of what we did in the first tutorial. So we defined what a pseudo-finite structure is. Just as a reminder, a pseudo-finite structure is a structure that is elementary equivalent to an ultra product of finite structures. Equivalently, it's a structure such that every first order sentence that is true in the structure has a finite norm. Okay. So, as I said before, this is more or less like thinking about asymptotic first order limits of finite structure. This is the idea. And we were discussing some examples from examples. So, the examples that we discussed here in the talk, there are many more. For example, include the random graph or these structures of vector spaces. We saw, for example, that the additive group of the reals was isomorphic to the product of cyclic groups with prime order, right? And we also talk about this couple of examples, which was like the infinite R regular tree, which is a graph without cycles such that each vertex has our neighbors, or the infinity, which is the same except that every vertex has its neighbors. Okay. Both of them were also examples of simple-finite structures. They were constructed as ultra products of graphs, right? And they also had certain like special measurability properties that we discussed in section in the part 2 of the tutorial. And just for completeness, some non-examples, we have dense linear orders, right? Because they are dense. There is no finite linear order that is dense, so that's kind of the point. We have the additive group of the integers, and the trick there, remember, is that there are certain functions that are definable one-to-one but not injective or vice versa. Sorry, one-to-one but not projective or vice versa. And just to put a field there, I put the field of the reals, it's not zero finite, also the field of the complex numbers is not zero finite. We also discussed last time that one of the key features of having zero finite structures is that you can have non-standard cardinalities for definable sets. Meaning that whenever you have an product of finite structures, for example, like this one, and then you can take a formula even with parameters in the zero finite structure, you can ask about what is the cardinality of this definable set, which is the elements, the tuples in M to the X, such that the model values its formula. And that's going to be the non-standard limit of certain natural numbers. So you can just treat it as a non-standard real number, and then you can call this, I'm going to call it right now C phi A. So notice a couple of things that are going on here. First of all, okay, this is a non-standard real number. It's a non-standard natural number, but you can treat it as if it was a natural number. So you can divide by it, multiply by it, add it, whatever finite combinatorial parameter you want to do. That's the first thing. The second thing is, notice that this is actually depending only on the parameters in some sense. So you can think of this construction as either I'm taking the ultra product of finite structures and I'm just talking about ultra product of finite structures, or I'm taking what I call the counting pair, which is taking the finite structures with a sort of real numbers, both at the same time. Take the ultra products, then you have your favorite ultra product, and you have here the non-standard real numbers. But the good thing about that counting pair is that counting pair can talk about the cardinality in a definable way. Of course, you have to expand the language, and that's why I added these functions that are called C for cardinality or for counting, but they only depend on the parameters. Okay, and by the end, I'm going to go back to this construction because one of the main questions you can ask if you're a model theorist is, well, if you have a nice ultra product And on the other side, you only have the field of the real numbers, which is a tame structure. We have seen several talks. What is the level of tameness that this counting pair may have? Okay, but I'm going to come back to this later. So now I'm going to define multidimensional asymptotic classes. I know that's a mouthful. So let me start with the previous definition of it, which is the definition of asymptotic classes of finite structures. This is basically what started the subject of this kind of measurability, finite structures, let's say, and this is the setting of formulas and finite conditions. And let me just say the example of what is a one-dimensional asymptotic class. Okay, so remember that when we were talking about ultraproducts that were strongly minimal, so the finite structures that were strongly minimal, there was always this thing of saying, okay, for every formula, there are finitely many polynomials, which are the possible sizes of the cardinalities, and finally many formulas that tell you exactly which are the possible cardinalities. This goes more or less in the same way. It's just that you allow some randomness, you allow certain error terms. So let me just read the definition to see what it says. So you have a class of finite structures. We're going to say that the class is a one-dimensional asymptotic class, and you're going to see later what this one-dimensional refers to. If for every formula there is a positive constant, see, that depends on the formula, and there is a finite set of real numbers, think of them as measures, okay, such that these two conditions happen. So the first condition says, whenever you have a structure in the class of finite structures and a collection of parameters, either the definable set is very small in the sense of being uniformly finite, it has this uniform bound, or there is a measure such that, this inequality holds. If one can read this inequality in the following sense. So notice that when n is going to infinity, what this is going to say, if you divide by the size of n, is saying that the measure of this definable set, of the cardinality of this definable set, is roughly mu, right? Because what you're saying is that the size of the cardinality of the definable set is mu times the size of n, except for some error term, which is this c n to the 1/2. But when you divide by n, that goes to 0. Okay. So another way of saying this is for every formula, it has finally many possible measures. That's what we are saying. And you allow some error term. And the error term is decided to be this one for the definition of one-dimensional asymptotic classes. And not only that, but also for each one of these possible finally many measures, there is a formula telling you exactly which of the measures are to take. And depends only on the parameters. Okay. So far, so good. So there are a couple of criticisms you can do to this definition. First of all, why do you consider an error term instead of taking exact things as one thing that you can do? Like in all the examples that we have seen so far, the actual value is exact and it's a polynomial, right? In this case, well, it's not exact, you allow some error terms. This is the first thing you can say. And the second thing that you can say is why this is specific bound and another. Okay, why don't you consider anything that goes to 0 when it goes to infinity, right? Instead of taking this exact c and to 1/2. And so why is it called a one-dimensional asymptotic class? Basically because we're talking about possible dimensions for definable sets in one variable. Okay, so when I say here that either it is finite, uniformly finite, or has positive measure, notice that positive measure is saying dimension 1. Okay, and being uniformly finite is dimension 0. So you have dimension 0, dimension 1 for formulas in one variable. How can we change this definition? You can allow, for example, certain fractional values. So instead of taking this n to the 1, you can take n to the 1 over n, or 2 to the over n, or 3 over n for some fixed n. That gives rise to another definition similar to this one, same structure in the definition, that is called n-dimensional asymptotic classes, and was done by a student of McPherson, Richard Ellis. And what I'm going to talk about now is, well, I'm going to mention some examples, of course, but I'm just going to mention the more general definition they have now. So this definition is a definition that has passed through many recurrence and additions and stuff, but it's basically conveys the main ideas that the asymptotic class probably has. This definition is due to Sylvie Armstrong, Luca McPherson, Steinberg, and David Wolf. And the idea is more or less the same. You just get rid of some of the criticisms that the original definition has. And also the purpose was to include like a family of examples that the others didn't include. That was more or less the idea. So what is an R-dimensional asymptotic class? So you're going to fix a collection of functions that go from the structure to the real numbers. Okay? And when it goes from the structure, you can see already that it may depend on the cardinality of the structures, it may depend on the cardinality of certain distinguished definable sets. It may depend on many things that has to do with the structure itself. Okay? But the point is that you fix these functions from the beginning, and then you say, well, a class is R-dimensional, R multi-dimensional asymptotic, or R-MAC, or R-MEC for the other definition. So R-MAC for now is for every formula, possibly several variables, right? There are finally many possible functions which are going to be the sizes, let's say, and finally many formulas such that you have this kind of same behavior. Okay. So you have a very good control of what the final of the cardinalities of the final sets, with some possible errors there that I'm just going to say it goes to 0 when it goes to infinity. Okay, that's kind of the point. Those are the asymptotic classes, the max. And sometimes it happens that you can actually say that the cardinality of the final sets is one of these finally many possible functions. Then you call it a MEC, which is a multidimensional exact class. Okay. I hope you don't hate me for the choice of words. It's not my definition, so just bear with me. I'm going to try to say MAC as a big Spanish A and MEC for the other one. Okay. And it's important to notice here that this definition, it's a little bit different from this one because this one only mentions formulas in one variable, while the other one mentions formulas in several variables. But the point, and it's also one of the main lemmas that they use, and we use when we try to prove that something is in dimensional asymptotic class, is that it is enough to check formulas in one variable. Once you understand the possible sizes of the final sets in one variable, you can run up like an induction argument, and at the end, you may need to add certain like products. For example, think about polynomials, okay, or sums, but that's about it. Okay. So if you have, for example, a family of functions that works for formulas in one variable, just take the convex, the polynomials based with those values, and that's going to give you the possible sizes for formulas in several variables. Okay, so let me now mention some examples. First of all, a good non-example, as I mentioned before, the ultraproduct of finite linear orders, or the class of finite linear orders, is not a multidimensional asymptotic class or exact class. Why not? Because of the finiteness requirement in the cardinalities. Okay, I mentioned last time that when you consider the ultraproduct of finite linear orders, you basically can take any possible size that you want between 0 and the size of the structure. Okay, and that can be done uniformly because it can be done only with one formula. So what you can do for the proof is easy. Just consider your family of functions. At some point, hi has to be very far away from hi plus 1 for some I, and then just pick in the middle, and that's not going to satisfy the other term. Okay, it's very easy. But of course, there is also a very good example, and notice the gears here. So this is actually the seminal example. This is what motivated McPherson Steinberg to give the definition of asymptotic classes, which is, in short, that the class of finite fields is a one-dimensional asymptotic class. Okay, so this is a theorem to Zoe Chatsidakis, Dalman Chris, and Andrew McIntyre, and it says, well, for every formula in the language of rings, there is a constant, and there are finally many pairs that can be thought of as dimensions and measures, such that whenever you pick a finite field and you consider the definable set, the measure is going to be roughly one of these finally many possible measures with one of these finally many possible dimensions with this precise error term. Okay, what does the error term comes from? Well, this proof is heavily based on the land weight estimates for sizes of algebraic varieties in finite fields. That error term appears in that proof, and the error term also appears in this proof. And also notice that I mentioned these kind of error terms before when I was talking about value graphs. So just have that in mind for a second. Okay, so basically they prove that the class of finite fields is one-dimensional asymptotic class. As a result, any ultra product of finite fields will have SU rank 1, in case you know what that is. If not, I'm going to mention it later, so don't worry. Good. So this is the seminal example. The second example will be similar to the previous one, and it's the family of Paley graphs. Okay, so the Paley graph was defined last time. It was like x related with y if and only if x minus y is a square defined. Okay, well, non-zero square. So what happens there is that you have a similar term to Washington, right? That says the following. So imagine that you have two disjoint subsets of FQ, right? Then you ask how many points are related with all of the elements on one side and none of the elements on the other side. And they do an actual count on that number of points, and it satisfies this bound. This is the definite, I mean, this is the bound that they have in the proof. But notice that this looks like a constant depending on the size of Q and W, right? Q to the 1/2 and something that is constant. Okay, so it can be said as a constant times Q to the 1/2. This kind of point. And as I mentioned before, and also this is the key part to prove that every infinite ultra product of these kind of graphs will give you a model of the random. Okay. There are other properties that Paley graphs have. For example, there's something regular. There might be some other kind of combinatorial properties, but they're not so important. So this kind of result also tells us that as far as you know how to measure these sets and to ensure that they are non-empty, you can do whatever you want with the sizes. You can even delete edges, delete some vertices. As far as those sets are non-empty, the ultra product is going to be a model. Okay. Good. Some more examples. So I picked this first set of examples because they are examples that have like an algebraic nature. So they are heavily based on what we know about the sizes in finite fields. So Elves in his PhD thesis, he proved that the family of simple groups or finite fields with you fix a Lie type. So imagine, for example, SLN of finite fields or GLN of finite fields or these kind of groups. Those are going to be asymptotic classes. So in his thesis, he was like n-dimensional asymptotic classes for some n, depending on what is the dimension of the Lie group that you're thinking about. But that was more or less the idea. Also, talking a little bit about like how do you say that, about automorphisms in fields, right? Like operators in fields. Right, it has a nice example of a one-dimensional asymptotic class that was basically having a class of finite fields, fixed characteristics. So imagine that this f p to the n, change the n in some way. So it's actually certain special p, certain special powers of a given prime, and take the Frobenius automorphism. Okay, that he proved that it was a one-dimensional asymptotic class. Well, of course, the properties and the powers were important, but a nice point here is that well, the ultra product is going to be, of course, a finite field with an automorphism, and we have theories of algebraic clusters with automorphism, so it was a little bit resembling of this kind of proofs by Krzyzewski in this setting. Okay, and also Pedro Aguirre, who was also another student of Macpherson. I know he's now in the University of Mexico, but forgive me because I don't know precisely where he's located in Mexico. So he proved that there are certain classes of residue rings that are asymptotic classes. Okay, so he considered residue rings, and for example, if you fix the d, the power, and consider unvaried program on the ranks, you're gonna get something that is a d-dimensional asymptotic class. So for example, notice that if this equals 1, then you're talking about fields of cardinality p, which we know already that were one-dimensional asymptotic class. Okay, so the idea is that this power of the primes is going to give you certain level of how, I mean, what is the correct dimension that you have to measure, and not only that, but he also had some results about what, I mean, which conditions of these kind of powers can you have so that the ultra product is NIP or simple NIP. So I'm going to mention a little bit of that on the end. Okay, now some examples of, notice that I changed a couple of things. So these are examples of exact classes, not only multidimensional asymptotic, but these are also exact. And these have more of a combinatorial flavor in some sense. So one of them is the class of all graphs with bounded degree D. That's going to be an exact class. And of course, neutral products may have different theories. It's not like the dating graphs. They may have different theories, but all of them will be stable. Just in case you're wondering about that. Also, you can consider the class of finite abelian groups. That's going to be a multidimensional exact class. And the proof is very easy because we have a quantified elimination for abelian groups. So we have these results of 1-Minier that where she basically had some invariance from which you have quantified elimination for abelian groups. And then using that quantified elimination, just focusing on finite structures, they prove that this is an exact class. And well, I guess the most recent addition to this was this result that I mentioned with my student Melissa Robles. You basically considering any class of regular graphs such that the degree of the graph and the curve, the size of the minimum cycle is going to infinity. That's going to give you a multidimensional exact class. Not only that, but the actual sizes are going to be polynomials into variables. And this is what I meant at the beginning when I said that the function depends on the structure. Okay. So notice that in this case, these polynomials may depend on the size of the full structure and on the degree of regularity, which is the same as saying the cardinality of the most regular form. Okay. Good. Let me now switch gears a little bit and also mention something that I mentioned in my slide before, but now I'm gonna mention it in more detail, which is this business about pseudo-finite dimensions. Okay. So I mentioned that when you have a finite structure, you can consider the counting measure, right? And when you consider the counting measure, you can take the standard part and you get an actual real value probability measure. You can do mathematics. This is basically one. You can use all the results in measure theory to try to apply them to specific problems. You also have certain well-behaved notions of dimensions. Okay, let me just tell you that probably you have to be a little bit open-minded in the sense of they are not going to take integer values necessarily. They're going to take values in certain weird. Sometimes they are non-standard reals. Sometimes they're in a quotient of the non-standard reals. Which will look a little bit like the classes of convex subgroups that Dario was talking in her lecture, right? And you have real valid fields. But the important thing about dimensions, if you really think about this, of course, saying dimension 1 or dimension 2 or dimension 3 is an abbreviation, and it's a useful abbreviation that kind of links with geometry in the general context of mathematics. But the important thing about dimensions is to know whether your dimension is smaller than this one or bigger than this one. Okay. Sometimes it is not so important to know that the exact number, just knowing this dimension is bigger than this dimension. Okay, and that's more or less what this is good for. So, what is a finite dimension? Well, I'm going to measure this logarithm of the size of the cardinality. Okay, so I have a definable set, and I pick the logarithm of the size of the cardinality, which is nice, good. And then I'm going to quotient by the convex whole of the integers. Okay, so that's going to give me just like a group with certain ordering. But the point, the nice point here that I also emphasize here is that the actual value is not the important thing here is to know whether two sets have the same dimension. Okay, so imagine that you have the definable set X, definable subsets X and Y. They're going to have the same finite pseudo-finite dimension. If I only, well, by definition, the difference of the logarithms of the non-standard cardinalities is in the convex whole of the integers. But that actually means if you do some little basic computations, that there is an n, which is like a natural number, such that the size of y divided by the size of x is bounded above and below with these numbers in the natural numbers. Okay. So let me just explain a little bit. So this means that log x, say, divided by log y is less than certain natural number. Okay. Yes. Different marker. Different marker. So imagine for the moment that y is contained in x, just to simplify the calculations. So log x divided by log y will be less than. Sorry, this is what I meant to write. This. Basically, want to prove this is less than n is bounded by some actual natural number, And then this is when you make the calculations, right? Because then you apply this, and you're basically saying that. So let's see, it's going to be e to the c, that is less than some n on one side, okay? So I'm saying as a subset of x, y is big enough, right? And also you can do the opposite, right? Just consider the other quotient. You're going to have e to the minus here, which is bigger than some 1 over n. So in some sense, having the same pseudo-finite dimension means you are commensurable, okay? Your sizes are comparable in some sense. Or the measure is positive, the countermeasure is positive. That's another way of saying it. This is one kind of pseudo-finite dimension, and another kind of pseudo-finite dimension is the coarse one. Actually, there are many coarse pseudo-finite dimensions. So I guess the most important of it is when you fix the definable set that is going to be important for you for some specific reason, and you just measure everything. Okay. So this has a little bit of the same flavor as, a more similar flavor to the dimensional one usually has, because basically this is going to be the standard part of this quotient of logarithms, but it basically says that the size of x is approximately the size of s to the delta, which is where this is the coarse dimension, okay? Which is more or less what you expect, right? If you're comparing the terms with s, then having dimension 2 means having size s to the square. More or less. Good. So, why do we call it pseudo-finite dimensions? Well, we call it pseudo-finite dimensions because they have certain properties and what might expect from a dimensional operator. That's why we call it that way. And this was defined for definable sets, but if you are willing to take certain completions in the non-standard reals, you're going to even have the definition for definable sets in the easiest way. So you basically have, as an implementer was saying in her lecture, you have an infinite intersection of definable sets. Those are type definable sets, and the dimension of that is going to be just the infimum of all these possible finite dimensions of definable sets you were having. Okay. So you can take these infimums, then you can define, of course, the dimension of a type or a certain set of parameters as the dimension of the corresponding type definable set. And these are the properties that I was mentioning before. Well, that I was referring to before. So the dimension of the empty set is always minus infinity. Dimension of a set is positive if and if the set, sorry, dimension of a set is 0 if and if the set is finite. Dimension of the union is going to be the maximum that's expected. Dimension of the Cartesian product is the sum. Perfect. Dimension of descending intersection of definable sets is going to be of type definable sets even is going to be the infimum. Nice. And this is probably the most useful one. So this is a sort of like Fulvini-like property for dimensions. So it basically says whenever you have a function, I guess I'm going to assume that it's projected just for the sake of sanity. You have x, your function goes to y, and you know more or less what is the size of each fiber, and is less than gamma in dimension, right? And you know what is the dimension of y, then you should know you should at least have a bound dimension of x. The dimension of x should be the dimension of y, or the image in this case, plus this dimension of fibers. Excellent. And the important thing is that, of course, they're defined for any program that you can imagine and find the structures, but in certain specific examples they behave really well. So if you consider, for example, this example, the product of the finite fields, you get by this Chatzirakis one and this McIntyre theorem that these holds. Okay, so I'm just taking one absolute value and distributing this mu on both sides. So you have that the kinetic definable set is more or less mu times d times f to the I and to the d with this error term and also with this error term, divided by the size of the structure, which is this. And then this, because of the definition that we had before, says precisely that the defined dimension of this object, the definable set, is the same dimension of this of this f to the d whenever the measure is positive. And when the measure is 0, well, in the one variable case, we have a finite set. Okay. So I only mentioned this fine dimension because, of course, it takes value in this weird group. But if you consider the coarse dimension, the actual value is going to be p. So Also works well. Good. So, okay, we went back to finite structures, go back to infinite structures. What happens if you consider properties under the product of infinite structures? How do they behave? How do they relate with the properties in the class? So we saw before that every strongly minimal pseudo-finite structure has these nice measurable properties, and in fact, if every product of a class is strongly minimal, that's enough to show that the class is one-dimensional asymptotic. And also, the other products of one-dimensional asymptotic classes are super simple of SU rank. So SU rank, as I mentioned many times, is a sort of crude dimension defined in arbitrary theories. Okay, they behave really well in the case of super simple theories, but one can show that this actually corresponds to SU rank 1. And more generally, consider n-dimensional asymptotic class of closed dimension. The SU rank goes from 1 to n. So basically, this numerical behavior is telling you something about the model theoretic properties of various products. Okay? How do you prove this? Well, in essence, I mean, this is going to be a very rough idea, but the SU rank is defined as change of something that is called dividing. And the point is that each instance of dividing is witnessed by a drop of dimension. Okay, as in most of the nice examples. So every time you divide, you drop dimension. If you can only drop dimension n many times, then you can only divide n many times. That would be SU rank 1. Okay, and when you now consider this general setting of multi-dimensional asymptotic classes, is not simple anymore. There might be examples that do not have this definition of simplicity, but they still cannot define infinite linear orders, which is the non-example that we have at the beginning. So one main feature here is that once you can define infinite linear orders, then it's not going to be the ultra product of multi-dimensional asymptotic class anymore. Good. Okay, so let me just check a bit how much time we have. In case they want to jump or just stay here. Like what? 15. Good. So let me just mention a result in, well, a conjecture in combinatorics. Okay, going back to simplifications. So we saw in the first lecture that, well, there was this theorem of Erdős that basically said that the Ramsey number of k equals 2 to the k half, what this means is that there are graphs of this cardinality that do not contain homogeneous sets, cliques or anti-cliques of size k. Okay, so one way of trying to read this is that in general, if you consider any arbitrary graph of size n, finite, what you should expect the size of the biggest homogeneous set that you could have here, you should not expect it to be bigger than log n, more or less. Okay. So notice that this k is in the power here. So more or less the idea is that if you have an arbitrary graph, no extra conditions, no whatever, the size of the biggest homogeneous set should not be that big. It should be logarithm of n. Okay. And that was the general result. But then the question is, what happens if you try to add a little bit more structure on the graphs? Okay. So after many trials, Erdős and Heinel published a paper when they stated this conjecture. So we're going to fix a finite graph H, and we're going to consider the class of all graphs that avoid H as an induced subgraph. So imagine, for example, if H is a triangle, then we're talking about triangle-free graphs. Or, well, this. If H is just one edge, then we're talking about empty graph where there are no edges. That's okay. And the point is that they conjecture that for a given H, there should be a number eta of H, which is positive, real. Imagine, for example, 1/2 or 1/3, no less, such that whenever you consider an H-free graph, it should contain a clique of size G to the eta of H. Okay, a clique or an anti-clique size G to the eta of H. So, in other terms, in other words, what this is saying is that even though the general case, the biggest homogeneous set that you should expect is logarithm of it, when you consider Hg to be H-free, this should pass from logarithmical to sub-polynomial. Okay, so the bound should be a little bit like n to the 1/3, for example. This is the difference the size of the homogeneous set that you're getting. Okay. So basically, you should get bigger homogeneous set if you impose the structure on the class. And the structure that impose is this one, between H3. Okay, this is a conjecture that is very close to my heart in the sense that when I saw it, I was studying finite dimension and said, oh, actually, this looks like a finite dimension in some sense. Okay. So one can try to prove this conjecture. And of course, I mean, there are many things to say about this conjecture. I'm just going to say I'm just going to give a few remarks. First of all, the conjecture is known to be true in all graphs of cardinality at most 4. Okay. So if the cardinality of H is less than or equal to 4, it's proved. Of course, there are certain special cases. For example, if H is a complete graph, then it's proven. If the empty graph is proven, whatever. Also, for example, the conjecture is not known yet for the cyclic graph for the pentagon, let's say, and not even for the path of 5 elements, which is weird. Okay. Probably the last couple of more striking results in this area, like towards proving this conjecture, is a result of Maria Chernovsky in 2012, if I'm not mistaken. It says that there is a specific graph for which the conjecture holds, which is the Wood graph. Okay, so the Wood graph is, well, as you may imagine, it's a graph on 5 vertices that is like this. Okay. So whenever you are rule free, the conjecture holds. Not only that, you have a specific calculation on this eta, and that's going to be 114. Okay. Of course, I mean, one of the most striking results in this area should not be this specific graph has, right? The point is that this specific graph was sort of one of the main combinatorial obstacles towards this kind of result, which is I mean, this is the statement, but it says basically that almost all graphs satisfy the conjecture. Okay. Whenever you fix an H and you consider the class of all H3 graphs, most of the graphs contain big definable sets, big homogeneous sets, big cliques or big cliques. Okay. So good. This is what we know about the conjecture. What does it have to do with Ultra products? Well, sometimes when you have a difficult conjecture, what you can do is just to make the conclusion of the statement as a definition and try to do somewhere else for the same kind of behavior. So you can define for a fixed class of graphs, right? You can say, what is the Erdős-Shannon property for this class of graphs? And it basically says, well, it's going to have the Erdős-Shannon property if there is a real number positive such that any graph in this class contain cliques or anti-cliques of this given size. Okay, so it's a polynomial in terms of the size of the graph. And the point here is that, well, it's now an arbitrary class of graph. It doesn't have to be the H3 graphs anymore, so you have a little bit of room to play with. But the good proposition here, which is actually not that difficult to prove, is that this statement, having the Erdős-Shannon conjecture for a specific graph, is equivalent to a statement about the ultra products. Okay, so a class of graphs is going to have the Erdős-Shannon property if and only if every infinite ultra product of graphs will have internal or definable, if you wish, homogeneous sets of big cores to the finite dimension, positive cores to the finite dimension. And the proof is actually very easy. So as I mentioned, this cores to the finite dimension takes values between 0 and 1. Okay. Well, because X is a subset of n. Well, it should be A, sorry. But the point here is that if you know already in the finite structures that there are big homogeneous sets, then this is a different concept. If you know that in the finite structures the sizes of these elements are bigger than the size of certain graph Gn to the 1 over 4, for example. Okay. Then what happens is that should be witnessed in the limit. So in the limit, if it is always 1 over 4, delta of A, delta product of these ANs should be bigger than 1 over 4. The coarse dimension should be bigger than 1 over 4. So how do you prove such a statement like this? Well, assume not, then for example, well, this is in one direction and in the other direction. Suppose that every infinite product has this kind of big homogeneous sets, okay? And this is positive. You use a compactness argument to show that actually being positive is being bigger than certain specific real number, actual real number. And then you pull down two structures and you get that this kind of bounds on the structures. That's more or less the idea. So it's actually a very good exercise once you have seen the previous programs from the second lecture. Good. So probably most authors have said something already about this class of graphs, and that's actually true. So this is a theorem. It was proven. I mean, it's an easy corollary of the results of Maneras and Shela on the regularity for stable graphs. It's a very nice paper. It uses model theory, but you don't need background in model theory to read it. You probably need background in model theory to understand why these ideas are put there. I mean, it's very, very well written. And so it's an easy corollary of these results, but in the form that I mentioned here, it was proven by Chernikov and Starchenko in 2016. So using zero-defined dimensions. What does the theorem say? The theorem says the class of m-stable graphs has the additional property. So what does it mean for a graph to be m-stable? It means there are no vertices a1 to an. Imagine the a's here below and the b's above, such that ai is related to bj if and only if I is less than j. So you have these kind of factors. Okay. Between the AIs and the BJs, you have this kind of factors. So this is not, I mean, this condition here doesn't say anything about the possible edges between the BJs or between the AIs. Only says what happens in this diagram, in this part of the graph. And this is a well-known, I mean, a well-understood class of graphs, which is called half graphs. Okay? And it was known for a long time that you have, when you have the similarity regularity lemma, you have this decomposition of the graph into sets of vertices, such that most of the pairs were regular. That was kind of the point of similarity regularity lemma. But most of the points cannot be improved to all of the pairs being regular because, well, you have this class of graphs. This was kind of the main example. But that once we know that being stable is not having this for certain n, that's what that stable class of graph is, then the canonical counterexample was not a counterexample anymore, so probably you get a better result, and that's precisely what happens in this result of condensation. Okay, so good to read. And also, this also takes us back to this geography of the mathematics that I was mentioning at some point in the second lecture. It's like, what is this? It's just there are certain properties like NIP or dependence, NTP2. I mean, Shela is the creator of this kind of names. Stability is another name. Simplicity is another name. And you have these kind of behaviors. There is a very well behaved corner here, which is the stable part. There is an even better behaved corner here, which is some minimum. Okay. So usually, what you can do is try to figure out what are the structural properties of certain object that makes it tame, meaning having these kind of properties, or untamed, meaning being outside of these properties. So, for example, you can ask why the random graph is simple but not stable. What does it make it unstable? Well, because you can find this kind of graphs, right? This is kind of the point. And why these linear orders, linear orders are not stable? Well, because you can codify these graphs. You can basically say A is related with B, if only if A is less than B, then you have codified these kind of graphs too. But the point here is that on this side of the spectrum, this seems to be a little bit like order-like in the sense of what I was saying in the second lecture, and this is like random-like in some sense. Once you cannot be random-like and you cannot be structure-like, you more or less should be in that. Well, okay, so I want to, how much time do you have? 5 minutes, perfect. So I would like to mention, I mean, to end this series lectures with a couple of remarks that basically it's a confession. There is a lot of things that I didn't talk about. Okay, that are still important. There's still projects ongoing, not only my projects, but for people that I'd like to mention because I think it shows how lively this area is. So let's start with something that I mentioned already as a general question, but this is a particular question. So there are different kinds of limits of finite structures. There are Frey-Limit, there are finite structures, inversely generic, and product. And one question that a natural question one may ask is, what is the relationship between all those possible limits, kind of limits that you can take, and even in the specific cases? So, for instance, Hugo Luis Mariano, professor in Brazil, and Francisco Miradia, they proved that any profinite structure, any inverse limit of finite structures can be seen as a retract of finite structures. Okay? If you know the definition of an inverse limit, you know that there is a definition that has to do with taking the Cartesian product and then taking certain piece of the Cartesian product. So in this sense, I mean, they define what this retract of the structure is, and in this sense, the base set is the same. It's just that on the size of the products you quotient by some equalization, on the size of the profinite structures, you restrict yourself to a smaller set. And in that sense is why this is a retraction of profinite structures. That was like done many years ago, and also Alex Krugman, much more recently, he was wondering how can you prove that certain of Frey class, I mean, general results such that if you ask something about the Frey class, whether or not the limit is zero-finite. Okay, that's kind of more the idea. So he came up with this definition of having a disjoint amalgamation property, which the class of finite graphs has it, but the class of linear doesn't have. Okay, and the point is that he showed that this condition was enough to show that the Frey class, the Frey limit was zero-finite. Okay, the proof is more or less the same as the one that you did for the random graph. It's a probability argument, and the point here is that this disjoint amalgamation allows you to make a better counting argument, and that's why this is fine.
That's for every n?
Yes, having disjoint amalgamation for every n implies that you have the limit of the process is going to be this. Okay, and there is also genetic limits. So, for example, there is this result of originating from Shella Spencer, and there are also results of Wagner Shella. That says that, look, there is a good 0-1 law for graphs. Okay, that's very well known. But if you restrict yourself, you consider this probabilistic model when you consider n vertices, and the probability of a pair being an edge is 1 over n to the alpha. Okay, for some alpha between 0 and 1. So notice that this is going to 0. So the larger the graph is, the more difficult it is to find edges. So Shella and Spencer show that there is a 0-1 law, and in fact, later Wagner and Shella proved that not only is 0-1 law, but it corresponds precisely to the Chomsky genetic ab initio construction. Okay, so if you put those results together, it says, well, the probability of a sentence being true is going to be 1 if it's true in this genetic limit, or 0 if it's true. Okay. So this is enough to show that this M alpha for alpha irrational is pseudo-finite. Okay. But now the question is, can we approximate it with a nice class of finite structures? Is it a multidimensional asymptotic class? Okay. So results that were presented last week by Alexander Weinable show some like progress in this direction. So she has like a partial proof that shows that not only they are pseudo-finite, but they can be seen as interproducts of certain asymptotic classes. Okay. Also, well, there is continuous logic. You can ask for a same definition, well, similar definition, what does it mean to be pseudo-finite in continuous logic? So you can say, okay, well, a metric structure is going to be pseudo-finite if whenever you have a sentence that has value 0, remember that 0 in continuous logic is like true, then you can approximate it not only the sentence, but also the truth value. So for every epsilon, you have finite structures so that the value of this sigma is less than epsilon. Okay. Some examples of this kind of metric structures, Hilbert spaces are examples, atomless probability algebras are examples. And the key feature here is that since you are now allowing to change the metric in the metric spaces, that give you a little bit more room to have meaningful mathematical structures. And what I mean with this is, for example, is over here. So you have a base linear order, which we know, of course, this is not pseudo-finite because it is dense. Okay, but now you can ask, what is the truth value of the sentence being dense? Okay, and the point here is that you can make it as close to 1 as you want if you just change the metric. You can think, for example, of the elements 1 over n, but then the distance between two consecutive elements is 1 over n2. Okay. So what happens then is that you get into your product, which is geometric with your product, and things that are the successor are negligible because they are at distance zeros, which is the same point. So you get again a density error. That's why, for example, atomless probability algebra, we know that any atomless Boolean, every finite Boolean algebra should be atomic, right? But you can be atomless, that's going to be an infinite structure, and be approximately listed by finite atomless algebras, as far as the atoms are very close to the minimum point. That's the only thing that is in it here. So, big conjecture here. We don't know still if the resonance field is zero finite. That's it. And also, there's this line of research, which is the binary for subfinite structures. So if you go back to this map of the universe thing, or like this kind of Chelakian properties, you can ask, okay, these are the examples, these are the counterexamples, these are the relations between them. What happens if we're just talking about subfinite structures? Okay? What kind of counterexamples appear or new examples appear? And the point I want to mention this in a very easy way. So for a strongly minimal pseudo-finite structure, every strongly minimal pseudo-finite structure is going to be locally modular. So it's going to be like a vector space. So these examples of fields do not appear in this context, even though the complex field is in this context. It is not pseudo-finite anymore. Not only that, there are no fields in that. Okay. Or for example, this one. You have something that is dependent on a categorical, then it has to be stable. And the proof is very easy. The proof is like, first of all, being NIP not stable means you have a linear order. But since you're pseudo-finite, the linear order must be discrete. And once you have a discrete linear order, it has too many two types. Okay, so it contradicts the fact of being omega categorical. That's very a very simple proof. So it was like folklore result, like somehow everybody knows this, but the proof that the complete proof appears in this paper of Alex Krugman that I mentioned before. And the big conjecture that also appears here basically says, well, if you're pseudo-finite and omega categorical, you should have a nice behavior. Perhaps should be one of these properties, which is MSP1. So this is a theory. I'm not going to mention it because it will have too many words. So let me just mention this one, which is a theorem from Bello Aguirre in 2019, where he basically considers superproducts of finite residual rings. Okay, always a finite residual rings. The only difference is this n. What kind of things can I do with this n? Okay, and there are many cases, but if you just mention as an example. So, for example, he showed that if you consider the superproduct out of the primes, but you fix the power. So imagine, for example, the power is 3, so it should be 2 to the 3, which is 2 to the 3, 3 to the 3, 5 to the 3, etc., etc. So you vary out the primes and you fix the power, then it's going to be simple, not only simple, but super simple of your rank B. Okay? That's one point of attack. Another point of attack is, okay, I'm just going to allow, I'm going to fix a prime, but I'm going to allow the values of the power. Okay? Those are going to be NIP, but not simple. Okay? Then you can say, okay, well, what happens if you allow a lot of primes and start thinking about, but like a fixed number of primes, not too many primes, but you allow the powers to grow. Then you're in the NTP2 case, which covers both simple and NIP. Okay, and if you're just being random and you can take anything, you don't have any bounds, well, there's going to be NTP2. So this is a nice specification of how the products of the residual will look like if you consider different opportunities of powers. So this is more or less the map, and I'm just going to finish with this sort of underlying philosophy, which is okay. We talk about the geography of mathematics. So a geography of 10 fragments or 10 classes finite structures should give you some insights on finite model theory and also some more applications for experimental methods. And that's kind of the philosophy that is going around. Okay. So that was the end of the lecture. So thank you very much. I'm going to give you some references. Thanks.
Any questions?
Yeah, so I know that no problem about distinguishing SOAP 1, SOAP 2, and SOAP 3. So We
Yeah.
know that there are at least two classes, but we don't know that there are find an example, examples to distinguish them. Do you think that your methods something else?
Well, I think I can do better. This is because there are no known examples, probably asking for us to find what would be more difficult. I guess there are examples that are SOPN and not SOPN plus one or vice versa.
Yes, but that's for above 3.
That's above 3. And no, I don't know of an example that is like SOP3, SOP2.
So this is for the first 3, so far, so good, so 3.
Yes.
To distinguish that, that has been open.
But it's still,
It's still open.
Yeah.
But I guess if your conjecture is to have something to say.
I guess. Although this is my conjecture, it's Alex's conjecture.
Okay, so the conjecture.
Yes,
is that-
conjecture. I guess you were gonna say something about this, or?
Yeah, so.
Yes.
Scotty Muchnick, that's a paper on the archive, solving half of the SOP. Difference, I think it's n SOP 1 is equal to n SOP 2. Yeah, so I think at least half of the questions seems to have been solved.
Oh, very nice. This is.
Yes, about a month ago.
Okay, so I just think it's.
Well,
So if there's any questions, I'm Salvador to Dario. Next, the tutorial that will be evaluated now.